This is the solution to projectile problem number 2, which is the angled projectile. So as usual, let's draw a picture. So first we have some level ground. All right, and we have to launch the missile at 36.8 degrees above the horizontal. So here's our 36.8 degrees above the horizontal, and we were told that this is 217.0 meters per second. Let's draw the path. It'll go up and come back down. So we're not going to change our approach. It is a projectile problem, so we're going to do everything we did in the previous problem. Let's set some axes up. X to the right, and in this case I think Y up would be a good choice. We're still going to do our starting and ending points. Start X, end X. We are looking for the range. Now this is what is important to see. When we are looking in the Y direction, look up and down. So as you look up and down, start Y and end Y are at the same point. So to visualize this, this is the equivalent problem in the Y direction of throwing a ball straight up and having it come back right to where it was initially projected. This is our picture. Let's start making our list. X direction, V0 in the X, V in the X, and V bar in the X are all the same. You either know it or you don't. The biggest mistake is stating that it is 217 meters per second. It is not. That is not in the X direction. 217 meters per second is projected this way. So we need to know how fast it is moving horizontally. We have to resolve this velocity vector into components. This is the x component of the velocity. From previous work, we realize hypotenuse, included angle, the x component is cosine. So the x velocity is 217 meters per second times the cosine of 36.8 degrees, which is 174 meters per second. So you have to really check to make sure you resolve a vector into components. So there's our Vx. Ax is still 0, and we are looking for delta x. Same equation as before. Delta x is V bar sub x times t. Delta x, 174 meters per second times the time. So like the previous problem, we're looking for time. We won't be looking for time in every projectile problem, but this one we are. So let's see what we have. In the y direction, we know the acceleration in the y by our axes, negative 9.80 meters per second squared. If you have a Vx resolved into components, you're going to have a Vy. If you have anything at an angle, you will have two. Remember, this is V initial y. Back over here again. V initial y would be 217 meters per second sine 36.8 degrees, which is 130 meters per second. Now, what is the key to this problem? Looking back over here in the y direction, we do know delta y. Delta y is 0. Remember, this is a displacement. It starts and ends at the same vertical point. And we're looking for time. So let's look at this equation. Delta y equals v0 sub y times t plus 1/2 ay t squared. Time to substitute in. Since we do have a 0, we won't have to use the quadratic formula. 0 equals 130 meters per second times t. So 1/2 times negative 9.8, we can put that right in, minus 4.90 meters per second squared, t squared. So how do we get t out of this? We don't need the quadratic formula. This can be solved by factoring. What does that mean? 0 on the left, let's factor out a t. When you do, you have 130 meters per second minus 4.90 meters per second squared t, all equals 0. So we now have the zero factor property. What this says, we have two factors multiplied together to give you 0, which says t equals 0, which is this one, or 130 meters per second minus 4.90 meters per second squared, t equals 0. We'll throw this solution out and solve this other one for t. T is 130 meters per second divided by 4.90 meters per second squared, which gives us 26.5 seconds. And now we can substitute that back in over here, and we will then get, for delta x, 4610 meters to 3 significant digits, and that is the solution to the problem.